Okay, what if our most basic assumption about reality is just wrong? Today we're diving into a wild theory that says the universe, I mean everything, from the tiniest particle to the biggest galaxy, isn't smooth at all. Instead, it's infinitely rough, complex, and fractal. And look, this is one of those single ideas that could literally rewrite everything we think we know. So let's get into it.
Yeah, it really all boils down to this one simple question. See, for centuries, pretty much all of physics has been built on this one core idea, that if you could just zoom in far enough, space-time would be perfectly smooth and continuous. But what if that's just not true? What if that whole foundation is wrong? What if, no matter how deep you dive, reality just stays jagged and complex?
All right, so here's the plan. First, we're going to dig into this idea of a rough new reality. Then we'll see how that roughness might actually create the laws of quantum mechanics from scratch. We'll even look for its signature out there in the cosmos. After that, we'll tackle how it completely flips our idea of gravity, how we could actually test this whole thing, and finally, what it all means if the universe is basically running on a kind of cosmic source code.
Okay, so our first stop is the big one. We have to completely abandon the idea of smoothness. And I want to be super clear here. This is not some minor tweak. This is a total paradigm shift. It's an idea that challenges the absolute mathematical bedrock of both general relativity and quantum mechanics.
So, the technical term for this is non-differentiation. Sounds complicated, right? But the best way to get your head around it is with a really simple analogy. Imagine trying to measure a coastline. If you use a huge kilometer-long ruler, you'll get one answer for its length. But what if you switch to a 1-meter ruler? Well, now you can get into all the little nooks and crannies, and suddenly the total length is way longer. A non-differentiable space is just like that coastline, but for everything, for paths, for time, for reality itself. It's just infinitely detailed, no matter how close you look.
And this table, wow, it really lays out just how massive this shift is. In the classical world we're used to, space-time is smooth, and a particle follows one single predictable path. Easy. But in this fractal space-time, the geometry is rough, which means there's an infinity of potential paths a particle can take. And that has this weird side effect on velocity. It's not just one number anymore. But here's the absolute kicker, the most important part. Quantum laws stop being these weird arbitrary rules that we just have to accept. Instead, they just emerge. They pop right out of the geometry itself. So how on earth does that actually work?
Okay, this is where the theory makes its first, truly extraordinary claim. It says that all the weirdness of the quantum world, the uncertainty principle, wave-particle duality, all that stuff, it's not actually strange at all. It's just the perfectly natural result of trying to move through a rough fractal medium.
So how in the world do you get quantum mechanics from just a jagged line? Well, it's this beautiful chain of logic. Step 1, you just accept that a particle's path isn't smooth. Because of that roughness, at any single point, the particle kind of has two velocities, one looking back from the past and one pointing forward into the future. Step 2, the theory combines these two velocities using a cool mathematical tool called a complex number. And here is the absolutely mind-blowing part. When you write down the equation for the simplest possible motion, literally just a particle coasting through this fractal space, the equation that pops out is the Schrödinger equation. The cornerstone of all of quantum mechanics just appears. It's not a rule you have to add in. It's derived directly from the geometry.
So let this sink in for a second. The crucial takeaway here is, all that quantum weirdness, it might just be what simple inertia looks like in a fractal universe. A particle isn't behaving randomly or jumping around mysteriously, it's just trying to follow the straightest possible line through an infinitely complex, jagged space.
Okay, I know what you're thinking. That is a beautiful, elegant idea. But is there any actual evidence for it? Well, to find out, we have to do the complete opposite of zooming in. We have to zoom all the way out and search for the universe's fractal signature in the way galaxies are arranged across the cosmos.
You see, standard cosmology, our best current model, predicts that on the very largest scales, the universe should be pretty much smooth and uniform. But that's just not what we see. When we actually look, observations show this persistent fractal pattern in the cosmic web of galaxies. And this chart shows something even more fascinating, how that pattern has actually evolved. The younger, bluer galaxies, the ones that are actively forming stars, are arranged in a much more complex, fractal structure than the older, redder galaxies. And if we look really far back in time, to the early universe, that complexity just plummets. It's like the universe has been growing more complex over billions of years. And then there are these
anomalies. These little bits of data that just don't quite fit the standard model. The most famous one is this bizarre alignment we see in the heat map of the early universe, the cosmic microwave background. It's so weird, it even got nicknamed the axis of evil. Now, statistically, there's about a 9% chance that this is just a random fluke. And, that's not impossible, but it's definitely high enough to make a lot of physicists really uncomfortable.
But what if it's not a fluke at all? This fractal theory has a different explanation. It suggests this alignment is actually a kind of geometric memory, a fossil left over from the universe's very first fractal structure, permanently imprinted on the fabric of the cosmos.
And this theory doesn't just stop with quantum mechanics and cosmology. Oh no. It also proposes a completely radical new origin story for gravity, and, well, all the other forces of nature too.
Okay, this is where the theory gets just incredibly elegant. I want you to imagine a single, fundamental field of what you might call informational potential. The theory basically says that time itself is just the first ripple, the first derivative of this field. Gravity? That's the second ripple. And all the other forces, electromagnetism, the nuclear forces, they're just higher and higher frequency ripples on top of that. It suggests all of known physics could just cascade out of this one single source.
Now, for any of this to work, you have to completely rethink what the vacuum of space is. It's not empty. Not at all. This theory sees it as a real physical medium, something called a dielectric that can actually store energy, almost like a universal capacitor. It's not nothingness, it's a sea of pure potential.
So here's the bottom line. This redefines gravity completely. In this picture, a massive object like the Earth isn't curving space-time in the way Einstein described. Instead, it's creating this deep well in the potential energy of the vacuum itself. So what we feel is gravity? It's just other objects sliding down into that well, always trying to find the lowest possible energy state. Look, a theory can be as beautiful and elegant as you want, but if you can't test it, it's not science. And this is exactly where the fractal model makes the jump from cool philosophy to hard practical science. It makes several very specific, very falsifiable predictions.
So it makes 3 key predictions we could actually look for. First, it predicts that at teeny-tiny, sub-millimeter scales, gravity won't follow Newton's law perfectly. Second, it says we should see particle interactions start to mysteriously slow down at extremely high energies. But it's the third prediction that is by far the wildest, and also the most testable.
So the theory suggests that it might be possible to build a device that taps directly into the energy of the vacuum. But here's the completely bonkers part. Every single engine we have ever built in the history of humanity gets hot when it runs, right? This device would do the exact opposite. For it to work, it has to get colder.
Yeah, it would essentially act as a gravitational refrigerator, literally sucking in thermal energy from its immediate surroundings in order to perform work. I mean, think about that. If we could actually build something like this and measure that cooling effect, that would be the smoking gun. It would be definitive proof that the vacuum isn't empty, but a physical medium that we can actually interact with.
All right, so let's wrap up by looking at maybe the deepest implication of this entire idea. Because if the universe is really built on a recursive fractal pattern, well then the very nature of what physics is starts to change.
The laws of nature, as we know them, might not be these fixed, timeless rules that exist somewhere outside of reality. Instead, they might just be the output of some kind of fundamental computational process. And if that's true, then physics stops being about discovering laws and starts being about trying to reverse engineer the universe's fundamental algorithm.
And what's amazing is that we might already have the tools for this kind of reverse engineering, and they come from computer science. There's this concept called Kolmogorov complexity, which is all about finding the absolute simplest program that can describe something complex, like, say, the masses of all the fundamental particles. We could even use AI, using a technique called symbolic regression, to just feed it raw experimental data and have it spit back the physical equations that govern it. We wouldn't just be describing reality anymore, we'd be decoding its operating system.
And so, we end up right back where we started, with a question. This theory paints a picture of a universe that isn't just a random collection of different laws and particles. Instead, it's this integrated, evolving whole, all emerging from one simple, recursive geometric rule. So the final question is this. What if all the mind-boggling complexity we see around us, from the quantum foam all the way up to clusters of galaxies, is just the output of a single, elegant algorithm that we are only just now beginning to understand?